Hi, this is our fourth video and we're gonna talk about PLDs. In this case, I'm gonna start explaining what is a programmable array logic. A programmable array logic is part of the PLDs and it is formed by two elements, an or fixed array and arrays that are programmable. The difference that PAL has with the PLAs is that they are easier to program, but they are not like that flexible as the PLAs. This is an example of how does a PAL works. Generally, a PAL has 8 inputs, 8 outputs, and 8 sections. Each output is gonna have a buffer or inverter to obtain the different results that will be given by the OR array. In this case, we're gonna have 12 inputs and just 4 outputs. The values that are in this table were obtained from the truth tables of some equations that were in this example. But to make faster the presentation, we avoid that process just to explain how does this table works. As I said, the PAL is just gonna have 4 outputs. So the 12 inputs are gonna be divided in groups of 3. In the first group, we can see that the first input is gonna activate, or it's gonna use the inputs A, B, and the second input it's gonna have A tested, B tested, C in its original state, and D tested. Then in the second group, we're just gonna have A plus BCD that corresponds to the fifth input. Then in the third group, we're gonna have from the input 7 A tested B plus CD of the input 8 and from the input 9 we're just gonna have B and D tested. And the final group, here we add another input because the outputs allowed in this case were just 4. So if we wouldn't add this other input, we'll have a larger program that won't be that flexible to use in a different area. So here we add the input W in order to make smaller the equation of the fourth output. So here we're gonna use W plus A CD tested plus ABC tested in the image that we can see of the representation of this table, where, as we know, the diagram of the PAL, it's gonna be formed by columns and rows. Each row, it's gonna represent the inputs, and the columns are gonna represent the input.
I'm going to talk about a PLD, Programmable Logic Device. Well, the programmable logic device are based on text entry. So that means that it's most likely like a language programming, such as C or C++. But the only difference is this kind of softwares are dedicated only to build logic gates and processors, registers, shifters, multiplexers, and all kind of stuff in a single environment programming. So the advantage of this kind of servers relies on the test before the construction of the ICs, microchips, and processors. So in this kind of features that we can see on the PLDs, we can find a software that has certain characteristics. This is the case of the Harvard Description Language, HDL. This way to program has several characteristics. First of all, it has a design entry. That means like you have to put in text inside of the program environment in order to get the certain the desired logic gates, such as like any kind of program. We have keywords also such that means something for the program, and that's the case of the model. The model works such as the beginning of the program that tells the program where has to start. Also, we have the end model that says where does the program has to enter. An input and outputs. That means that you can program a microchip that has several inputs and outputs, or you design in just one terminal each one of them, such as inputs and outputs. And also how you can design it by sections, because you have a lot of inputs and outputs. You can terminate by numbers, by letters, and that helps the programmers to share information about the integrated circuit that you are making. Also, we have wire. That means that this input has to connect with this output, or with this gate, or with this process. The wire relates the inputs and outputs with the gates. And also we have the gates. In this case, we have three different logic gates. They are the basic ones, and, or, and not. The combination of each one of them makes another types of logic gates and allows us to more complex devices. In this kind of softwares, also we can find logic simulation that allows us, such as allows us to preview the program or the devices that are inside of, or we have to pretend to build in the real world. So this allows us to help maybe the disconnections, the failures, the errors that maybe the project has. So you can run run your program, your devices, and test them on real and in the software. Also, we have the logic synthesis. This means that you can determine it just by typing the numbers related with the wires and outputs if they have to connect. So that means if you have a gate that only has only one node in certain inputs or outputs, can determine just that that connection has to be there and not anywhere else. Also, we have timing verification because most of the uh, devices are made up of tiny, tiny devices that are transistors and really small devices. We have a time response of each one of them. So depending on the amount of tiny components, we can determine how long does it take this your program or your project to do certain tasks that are the purpose of the project by itself. And also we can find the fault simulation. This, this fault simulation allows us to the program maybe find the errors after the process of or the manufacturing of certain devices. And because these are really, really small devices and specialized tools and process, so maybe a tiny particle can be inside of these circuits. So then these particles, maybe like dust, can provide problems to the circuit, integrated circuit. So this kind of faults allows us to, okay, maybe we can simulate an error in certain parts of the microchip and see maybe the behavior that in real world should happen. So after you can prevent or manipulate your simulations with errors, you can determine in real world maybe the compatibility of matches with the errors that real devices have, and determine okay, this is the error you can find in maybe the corner of the IC, and the process is failing because of it is not clean enough that area or problem similar. Also, we can find the port list. The port list is a chart where you can find all the inputs and outputs and the gates. It's like a description page where all devices and inputs are determined by the programmer. So you can determine which one of them has several functions, how does it work, and you can find by each element inputs and outputs pins and the role are playing in the real work. So basically this is the process to programming a logic devices in a computer and simulate. This allows us to, between the programmers, shares information, maybe change, allows us to make change in the devices in order to improve them and also making better. Also, the server is public, so everyone can share and see what's doing. Thank you.
Hello, my name is Roberto, and now we're gonna investigate the PLDA architectures um, because they are so useful to look at various hardware choices available to digital systems designers because it should give us a little better perception of today's digital hardware alternatives that we have. As you can see, digital systems is divided in three categories, which are standard logic, ASICs, microprocessors, and DSP. Well, standard logics, we already saw them in the last videos, and now we're gonna be focused in the ASICs. Well, ASICs is divided in four subcategories, which are the PLDs, programmable logic devices, the gate arrays. We're gonna see what is a gate array inside a programmable logic device, and standard cells, full custom also. Uh, these last three is how a programmable logic device is made, the structure that is inside of them. Well, this is also this also uh, is developed into CPLDs and FPGAs, and then we have more types. We're gonna list now each of them and say some features, characteristics that they have, and how well we're gonna try to explain how each work in a real circuit. Well, we're gonna start with the ASIC, but what is an ASIC? An ASIC is an application-specific integrated circuit, and that means that it is customized for a particular use rather than intended for general purpose use. Well, the maximum complexity possible in an ASIC has grown from 5,000 gates over to 100 million gates. That's a lot. And that means that modern ASICs often include entire microprocessors, memory blocks, including ROM, RAM, EEPROM, flash memory, and other large building blocks. Well, but how it is structured? Well, it has a full custom, uh, which is designed and it defines all the photolithographic layers of the device. Yeah, it has too many devices of different metals. And also, its custom is used for both that which are ASIC design and for standard product design. The benefits of full custom design usually include reduced area. That means that they are smaller, and they also have performance improvements through the years, and also the ability to integrate analog components and other pre-designed pieces. Well, we also have these advantages of the full custom design in an ASIC that includes the increased manufacturing and design time, increasing non-recurring engineering cost, and more complexity in the computer-aided design system, and much higher skill requirement on the part of the design team. Yeah, it is too actually it's too hard to mm, build an ASIC because of the thousands of thousands gates it has. All right, talking more in general, we're gonna list the most common um, logic devices that we have, and try to explain each of them. All right, in general, programmable logic devices, the PLDs are the key in technology for the future and digital systems. We already said that they are gonna be too useful. They are already too useful, but they will be more useful in the future for the digital systems uh, to develop more types of microprocessors, logics that we're gonna have. Also, PLDs can reduce parts in the inventory, simplify the prototype circuitry, shorten the development cycle, that means faster, reduce the size and power requirements of the product, and allow the hardware of a circuit to be upgraded easily. Um, we already see the major digital system categories, which are in the standard logics, the application circuits called ASICs. ASICs is one of the most common, and microprocessor digital signal processing, the DSP, is also a very common device. So we have ASICs and DSPs. The ASICs are devices that may be programmable logic devices, which has gate arrays, standard cells, or full custom devices. The PLDs are the least expensive type of ASIC to develop. Uh, as a summary, and simple PLDs contain the key element of 600 or fewer gates and are programmed with fuse, APROM, or AAEEPROM technology, which is in the category that we saw in the chart. Um, we have the high capacity PLDs, which is divided in, well, depending on its architectural, which is complex programmable logic devices, the CPLDs, and the field programmable gate arrays, FPGAs. All these are mm, categorized in the table that we have at the beginning. Finally, we got the the Altera CPLD that contains 128 microcells, each of which contains a programmable AND or circuit and a programmable register. That means that those are a lot uh, of gates, and it also has about 68 inputs and outputs.
In order to be useful, programmable logic must have both hardware and software components combined into a functional unit. All manufacturers of SPLDs, CPLDs, and FPGAs provide software support for each hardware device. These software packages are in a category of software support known as a computer-aided design, most known as CAD, like AutoCAD. Most specific software packages incorporate these elements in one form or another and process them automatically. The device being programmed is usually referred to as the target device. We must have four things to get started programming a device: the computer, the software, which normally goes in CD. Uh, More recently is most common to find the software by internet. And we need the cable, the interface connector or CPPI cable, and the device. The device could be now a microcontroller or a CPL, FPGA. Now let's see how these elements function. We have the schematic. All these parts we found it in the program. The program is making this automatically. Then once that we prove that the program works, then we download all the program to the device. The device by itself doesn't do anything. We need to know now how to program and make what we want in the device. Now we have to install the software, connect the cable, but before we start to connect the device or the circuit, we need to make sure that the device, that the program will be run perfectly and will have all that we want and work in the best way possible. Then Also, to connect normally the device, it's common to find in the market development card which can connect which allows to connect the device here, and then this has the interface, which now is most common to find one USB. Then once that we make sure that we make the program, now that we make sure that we had all this in a perfect state, we need to know how to program. We can control the device with many languages, which can be C, C++, Dev, but the most interesting way to program all these devices are the assembler language. The assembler language allows us to program the device in the most rudimentary, and that's all that we need. The software goes by hand with the computer. These software packages are known as a CAD, like AutoCAD. This computer-aided design. This allows us to work in an intuitive way to manipulate the controllers.
I'm going to talk about the programmation of the PLDs. Well, for this we first need to know from where comes the PLD, and well, we need to know about the RAM, the ROM, memory ROM, the PROM, EPROM, and the E square PROM. So we're going to see each one of these to know about the PLDs. First, the RAM. What does RAM means? RAM means random access memory. This means that you can access to each point of the memory just using the direction of the information that you need. The memory RAM works with electricity, and it needs to have electricity to keep working because it's made of capacitors inside of the memory. So when you turn off the light that is connected, the electricity, all the capacitors will discharge and you will lose the memory, well, the data that you have in the RAM memory. So when you use it, it needs to have always electricity, needs to be connected. And you can write and read from this memory that is not like the memory ROM. The memory ROM means read-only memory. It's read-only memory. This means that you only can read the memory. You cannot write in it. And this is because it just has outputs in the circuit. It doesn't have inputs or another pin where you can change all the information that the ROM has. Now we have the PROM memory. This memory works, well, it's a programmable read-only memory. And that means that you can program what you want inside of the memory, but you can just program it once. And this is because it works with fuses. And depending on which data you will need, you can overload the fuses that the PROM has inside, and then the fuses blow or melt, so they won't be able anymore, and the fuses that were intact can work as information for the prompt. This is this is like the ROM, but you can program what you want inside. And next we have the EEPROM. This memory means erasable, programmable, read-only memory. And this works with a small technology. You can program the ROM and you can erase it, but well, the EEPROM is like a small chip with a little window inside of the chip. So when you program it, the only way to erase it is putting the chip into a device that is like a little microwave, and it shoots infrared light. This is a chip that has like a little window inside, and you can see all the connections. And well, the only way to erase it is when you put it into a little microwave that shoots ultraviolet light into it, and after a few minutes you will have all the memory clear. This kind of memory came obsolete after the E-square prom. What does E-square prom means? It's electrical, erasable, programmable, read-only memory. So the way that the E-square prom works is the same that the EEPROM, but when you want to erase the data that you have inside the chip, inside the memory, you just need to put voltage in one pin, and all the data that the E-square prom has will be erased, and you can program it again and again and again all the times that you want. This is the advantage of this kind of chips. So to work with the PLD, a PLD works like a prom. So the PLD is an array of AND gates in the inputs and a fixed outputs, fixers in the outputs. So the AND array in the inputs, you can program it like a prom because they have fuses. So you can make a program, and when you have the program, you make with that program you can choose which fuses are you fusing of the AND array that the PLD has in the inputs. And well, you can just program it once. It's not like the another memories that we have that we can program it all the times we want. So you need to think it good before you program the PLD. Also, well, that was the PLD. In the PLDs we have a device that is called PAL. PAL device that is like a prom memory, and the PAL device works well like a prom because it has fuses in the array of AND gates in the inputs, and to program it you need to blow the fuses that you don't need and in the inputs, and it will passes all the memory, well, all the data you have, it will pass it through the output. And well, another kind of device that we have is the GAL. This works the same as the PAL, but it has the memory that it has inside works as a e square prom. So the PAL, you just can program it once, but again, it's like a PAL, but you can program it as many times you want because it has erasable memory, and you can make the rate that you want in the inputs and also in the outputs. That is an or there are fixes or so. Well, the gauge looks like more convenient, but the pill is the most used because it has, well, you just can program it once and for the thing that you want, and it's the most used in the factories and in all the devices.